If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong.
Okay, before I get started, I'd like to thank everybody again for viewing and for commenting and engaging. I know there hasn't been that much activity, but I expect there will be soon. So before I do get started, let me get my circle straight. I've made a couple of mistakes at the beginning of both of my first two videos regarding this. I'm not much of a narrator. This is the first time I've done something like this in my entire 25 years as a designer. So please bear with me. I know that what I've found as far as my problem is concerned is absolutely accurate, so if you just hear me out, do the math, and verify it yourself, everything will be alright. So again, I'm going to start where I started the last video. This is what we know to be pi, the circumference of a circle when the diameter is 1. Or you can take the circumference and divide it by the radius and get 2 pi, or you can take the circumference and divide it by the diameter and get pi. There's also some infinite series equations or formulas which converge to pi, and that is what we come to know as pi as we know it today. Okay. So again, I'm going to show this slide and point out, like I did in the last video, that when d is equal to 1, the circumference is pi. But pi isn't really there. I mean, it is, but you have 3.142. You don't have the exact decimal of 3.14159265, etc. And I pointed out that you don't see that in nature. But you do see a lot of values from the pi gradient in nature. In this case, when SW, being the synergy whole number constant, is set to 1, we have 3.142. So that was an example of observing something in the real world that we get from an equation that just drops pi out. It literally just falls out of the equation. There's no infinite series, and it's accurate to an incredible degree of accuracy when compared to the current model of pi. Okay, so we talked a little bit about Zeno's paradox, which I explained my thinking on this and how and why it pertains to pi. And the simple form of that is that I believe that we should be looking at how things grow and how they can naturally divide versus taking a arbitrary set length and infinitely dividing it. And I think that we're missing some information in doing it that way. So when we look at the radian, basically what my theory is that there has to be a proper way to figure out what's going on with pi. It shows up in so much beyond just circles, so it's not just the circle. My initial thinking with the radian was that this U, it acts as a tail, if you will. I've called it the triangular potential of a circle. I don't know how or quite what to describe of it, but essentially what happens is as you add more positions or more circles, this U will get closer and closer to the value of radius 1. It already starts off pretty close when we have 9 as the number of positions. We also have this interesting coincidence with the octoquadrians where we have 250.333 as the angle, the outside angle for the connection of what would be this third radian line. And the 333 can be explained by the +1 aspect of the octoquadrians if you caught that in the first video. And then we go over to when we actually place all 9 circles. And this is where you really see what's going on as far as U is concerned in this triangular potential of a circle, if you will. Again, I don't know, I'm still struggling with how to exactly describe it, but that's how I see it. And basically what happens is we have this 250.333 turn up again. And that gives us this strange multiple of psi pi, right? Where on polar angles, or sorry, polar numbers, when your number of positions is a polar number, such as 9, 18, 27, 36, 45, etc., you end up with this polar behavior that gives you a strange multiple of psi pi. It's almost exact, and it actually fluctuates between the different poles, or the different polar numbers. I'll also point out that this decimal 876 is the 4th octoquadrian. So there's definitely something interesting and strange going on as far as pi, radians, and octoquadrians. So now let's look at another curious feature of SciPy, polar alignment. Now, if we use a synergy constant, again, this is 1.62, so we're not a whole number constant, we can get something I call the polar alignment. And that is every time you reach a polar number, such as 9, 18, 27, 36, etc., by running this equation, the square root of the radius divided by the number of positions multiplied by the synergy constant, we actually get this reflecting polar number. So when there's 9 positions, we get 54. When there's 18 positions, we get 27, and so forth and so on. I think it adds a lot of weight to the argument that this is in fact how pi behaves. So what do we got? What do we observe about SciPy? It's an accurate and logical way of expressing pi. It has a comparative accuracy of an extreme value. It maintains a stable and accurate positioning with each orbit. The extremely small variations in the position match the behavior of pi almost identically. It's more efficient of a calculation than an infinite series for pi. And you have to question if SciPy is actually more accurate than the current accepted value of pi, because when you plug it into, say, the three-body problem, the Kepler-16, it centers the origin better. So that poses a question. And then, of course, you get the values of the SciPy gradient that more closely match what we observe in the real world. So I'm going to start showing you some modeling, and what you're going to see is I've run this equation and iterated more than 2 million times, and there's basically been 3 versions, I'll call them, versions of pi, or 3 different pi formulas, if you will, values of pi over the history of time, and only 3 are standing. 2 have almost perfect positioning, if not perfect position. And one, the number 3 there, the Z pi, I call it, Zhu Chang Z 480 AD, that's coming in at 3rd. It's got a little bit of distortion visually, but it's still holding its own in that exact position. So it hasn't morphed. And I'll show you what I mean by that. Okay, so let's actually get into it and start looking at it running in real time. So here's my, I'll just refresh this so we get an accurate depiction. So we have JavaScript math.py running here, and we've got SciPy running here. It's a side-by-side comparison. I've got all the values of the full equation broken down. The only difference between the two is that in all cases where pi is required, this version uses JavaScript.py. In all cases where pi is required, this version uses SciPy. Okay? So them are the rules, and this is the comparison. So we can see here, this is at the bottom, this is the deviation in position as it makes its orbits and places circles or positions. And then I'm going to start describing some of these values. Okay, so we got the number of positions and the radius. The radius of each circle in formation. So I can increase the radius or I can increase the number of positions. As we increase the number of positions, let's say we go to 18, which is a polar number. 1 and 8 are polar numbers. If we go down and we look at the polar alignment, the PA, it's set to 27, as I showed. Okay. We can also see that the SciPy multiple is just a hair over 2. It's a strange multiple. I'm not sure why it does this. I've got a lot to explore, but it's notable nonetheless. Okay. So we've got the size of U, which is I guess the final tail part that we talked about. Let's go back to our slide. This tail U, right? So we got our value of U. Okay. So I'll go to 27 positions. And again, we got our polar alignment, which is 18.18. It's a really interesting behavior. And I'm curious as to the connection between the radian, the octaquadrian, and pi. I think that with the synergy constant, there's definitely some very, very interesting behavior going on here that I think is worth a look. And there's, it's just that the accuracy is crazy. And then if you go here, this simulation, so here we have over 2 million iterations. And you can see here that this is the JavaScript.py, and here's SciPy. And they both look identical. Visually, they both look identical. You can go down the list, and all the values seem to be pretty much identical. Not quite, but they're very close. And then if you look at every other version of pi throughout history, you can see they're already broken, right? So the circle positions have basically shifted so much that you can't even make out the pattern anymore. And the only other one that holds a pattern is again, Zhu Chongzhi from 480 AD, which has a little distortion, but is still, it's stable. I mean, after 2 million iterations, it hasn't changed, you know, since basically the first 100,000 or so. And that's kind of stayed the same. So every other version of pi in history has kind of already collapsed on itself, right? Yet we have JavaScript.py, which is an infinite series version of pi, and SciPy, which is not an infinite series, and they both are performing exactly the same. So how did we get here? I mean, how did we literally get here? We went from starting with a problem. We wanted to figure out R2. That's all that I wanted to figure out was R2. How do I place 9 circles of information in such a way that they kiss with no gap in between? And what started there turned into, based on research that I had been accumulating over the last 4 years, turned into a set of variables which partially came from a new discovery of octoquadrian numbers, which nobody has been able to explain. Gave me a radian base constant that I call as the base of the radian. So I think that this best explains what I'm talking about as far as the triangular potential of a circle. This is, I don't quite understand it, but this is related to that. You know, you have your base radian of what it would be before you compress that slice of pie, if you will. And then, you know, we went through and we figured out what that compression is and what the tax would be to figure out the compression to give us an exact radian. And then from there, we literally one step away from an exact version of pi, or very close to exact. You know, the accuracy is remarkable. You know, we fixed our problem and controlled the gap, and we also, you know, mysteriously found 2 different orbits, one compressed and one expanded. We solved the original problem for R2, and then we find the full SciPy gradient using the synergy whole number constant. We test it on the 3-body problem, and we get a more centered origin on the Kepler-16 system. You know, from the beginning to the end, it's all very remarkable. And I think that, you know, what it really says is that, just like this says, if this is fiction, it's the craziest, most striking fiction you will ever see. With that, I'm going to leave you with a quote from one of the greatest minds in my mind of all time, Richard Feynman.
I want to concentrate from now on, because I'm a theoretical physicist, I'm more delighted with this end of the problem, as to what goes or how do you make the guesses. Now, it's strictly, as I said before, not of any importance where the guess comes from. It's only important that it should agree with experiment, and that it should be definite as possible, as definite as possible. But you say that is very simple. We set up a machine, a great computing machine, which has a random wheel in it that makes a succession of guesses. And each time it guesses a hypothesis about how nature should work, computes immediately the consequences, and makes a comparison to a list of experimental results that it has at the other end. In other words, guessing is a dumb man's job.